Welcome to Archive Mind, your memory palace for mastering difficult concepts where we turn complex topics into simple, bite-sized lessons you'll never forget. This is part 1 of the Bayesian Networks playlist, an introduction to Bayesian networks. Imagine a scenario where a team of doctors are faced with a patient experiencing a range of symptoms that points to multiple possible diseases. How can they accurately diagnose the patient? This is where Bayesian networks come in. Bayesian networks are probabilistic graphical models used in AI to represent a group of variables and their conditional dependencies. The network is represented by a directed acyclic graph, a DAG. In a DAG, there are three key types of connections to represent conditional dependencies between variables or nodes. These are serial, diverging, and converging connections. Bayesian networks are inspired by natural phenomena. These probabilistic models help in critical decision-making by modeling cause and effect relationships. This is an example of a simple Bayesian model called the Asia model. This model is used for diagnosing a patient with lung cancer, tuberculosis, and bronchitis based on some key risk factors, symptoms, and medical tests. This is another more complex example of a Bayesian model. This model is used to show how changing certain risk factors like smoking, diet, or exercise could affect the likelihood of developing heart disease. At the core of Bayesian networks is Bayes' theorem, a mathematical framework that describes the relationship between conditional probabilities, allowing us to update our beliefs about an event based on new evidence and to revise probabilities based on this new information. The theorem is stated as follows. The probability of A given B is equal to the probability of B given A times the probability of A divided by probability of B, where the probability of A given B is the probability of an event A occurring, given event B has already occurred. Probability of B given A is the probability of event B occurring, given event A has already occurred. Probability of A and probability of B are the prior probabilities of events A and B occurring independent of each other. By understanding Bayes' theorem, we can leverage Bayesian networks to predict disease likelihood based on symptoms and prior knowledge, update prior beliefs as new information becomes readily available dynamically, and handle uncertainty so we can work with incomplete data effectively. Moving on to the Bayesian network structure. For each node in a Bayesian network has an associated node probability table, where the parameters and conditional dependencies can be set and provided by either expert knowledge or automatic learning from data. Node probability tables, NPTs, also known as conditional probability tables, are used to represent the conditional probability of a node given its parent nodes. What do I mean by this? Well, think of NPTs as a table of contents for an ice cream parlor, which tells the ice cream machine what flavor to make based on your mood and the weather outside. The mood and weather are factors determining the likelihood of the ice cream flavor. These factors are usually decided and provided by either the expert knowledge or automatic learning from data. Bayesian networks excel when it comes to handling uncertainty, which is often present in real-world data. They also utilize probabilistic inferences to quantify uncertainties and represent conditional dependencies between variables to allow machine learning models to make more accurate, optimum, and robust decisions. As mentioned before, in a DAG, directed acyclic graph, there are three key types of connections: serial, diverging, converging. These are key whilst building the structure of a Bayesian network. These connections are all shown through direct causal links, shown by arrows between nodes. In the below Bayesian network, burglary leads to an alarm being activated. Think of it as an event A causes another event B to occur. This is a serial connection. A divergent connection as represented by an earthquake leading to alarm activated and radio news. A single cause affects multiple outcomes. There are no convergent connections in this Bayesian network, since no event happens as a result of two causes. An example of a convergent connection, though, could be a late train leads to a missed interview, and a traffic jam also leads to a missed interview. Bayesian networks have wide applications in various domains, one of which is the medical field, where Bayesian statistics act as powerful tools for biomedical informatics and medical decision systems. They're useful in understanding complex neurodegenerative disorders like Alzheimer's and Parkinson's by modeling complex relationships between biological, genetic, and environmental risk factors. But these Bayesian networks are not just limited to the medical field. They can also be used in environmental modeling, where experts and stakeholders' opinions are useful when modeling a problem or system. They can be used for risk assessments, where BNs can quantify the impact of risk factors for an environmental risk assessment and understand how variables influence each other, as well as assess the impact of different environmental factors such as pollution on ecosystems or health risk. Further applications of Bayesian networks can be used for bioinformatics, genomics, and even the law judiciary system, since Bayesian reasoning can help provide that rigorous method and improve the efficiency and fairness of the criminal justice system, as well as the accuracy of verdicts by enabling relevant evidence to be meaningfully evaluated and communicated. It can further help experts formulate accurate and informative decisions. Bayesian networks play an integral role in machine learning by addressing key challenges that traditional deterministic AI methods struggle with, since they work more like black boxes. Interpretability is often more useful in Bayesian networks, and its ability to intuitively support cause and effect relationships further help and show that Bayesian networks can be a powerful tool in predicting and describing classification based on the mathematical framework of Bayes' theorem. Many AI approaches rely on vast datasets to process the data, whereas Bayesian networks can work with small, incomplete data, making them practical for complex clinical decision-making processes where data may not be readily available. And that's a wrap. Follow Archive Mind for more bite-sized lessons that make complex ideas memorable. As always, drop down any suggestions for videos, and see you next time. Thank you.